We're going to talk about gravity today. It's very exciting to talk about gravity. I'm also doing a trick for you guys. You ready to see the trick? I have not had coffee, okay? I'm going to lecture 75 minutes without coffee. I've never done that before. This is a first-time demonstration. Here we go. You'll probably be able to understand me, what I'm saying. Okay, so we can't see the poster, but basically the first 2 days of this, Tuesday was all about circular motion. So we did kinematics, angular displacement, angular velocity, speed. Basically gave you formulas for those. Remember, there were sort of the rotational variables, theta, omega, and alpha, displacement, velocity, acceleration. And then there were the tangential ones that we care about, sort of the ones that are tangent to the circle, the tangential velocity, and the one radial to the circle, the centripetal acceleration. So jumping between those with concepts like period, that was what Tuesday was all about. So we'll be doing more of that today, because today we're doing gravity. And a big part of gravity is, of course, being in orbit. And we'll talk a little bit about orbits. And then we'll talk about why we're weightless. So this is a pretty good distribution here. We've got all three answers. If you ask people on the street, why are you weightless in space? These are the typical answers you'll get, except for B, which is correct. You'll get A and C. Okay? But we'll talk about why B is correct. I got a text question about the pledge. I do not answer any questions about the pledge except this one. I will answer this question about the pledge because by not answering it, I will answer it. Therefore, I will just answer it. For the pledge problem, is the mass is not given. Is this intentional? Yes. There you go. I normally don't answer pledge problem questions, but I figure I can't not answer that question. It's a catch-22. You caught me in a catch-22. Now get me in a catch-22 where it says, what's the answer to the first one? If you can turn that into a catch-22, I will have to answer it. Okay, so today, let's get this out of the way. Well, late people will get it wrong. Let's go ahead and put it up. Let's mute this. So today, talk about gravity. And we've sort of already talked about gravity. Although we talked about gravity near the surface of the Earth, what we're talking about today is sort of universal gravity. Okay, and this is more discoveries. Can we use calculators on the pledge? Yes. Yes. You can use calculators on the pledge. 2 questions about the pledge. I've broken the rules twice. Dr. Stinson is going to get me fired. Okay, so this is another big thing that Newton did was realizing that the reason things move near the surface of the Earth and drop, what causes that is the same thing that causes planets and solar system objects to move around each other. It's all the same thing. And this is what physicists love to do. We get very excited when we come up with one law that explains multiple things. That's like all we care about, some of us. So that was a really big deal. But the deal is it was more than just F equals mg. It was really universal gravity. That's what sometimes you'll see this topic called, universal gravity or gravitation, to make it sound fancy. Okay? So, it's an attractive force. Force between every pair of bodies, right, in the universe. Sounds kind of important, doesn't it? Yes. So if we're going to describe it mathematically, well, there's the non-mathematical description. Everything is attracted to each other. So now let's describe it mathematically. So pair of bodies, of course, I told you on the first day, a body doesn't have to be a body. It could just be anything with mass. So here is one thing with mass. We'll call M1. And here is another thing with mass. We'll call M2. Okay? So if you want the gravity between them, the gravitational force between them, you put them on an axis. And the great thing about 2 bodies is they're always on an axis. Right? You can always draw a line between 2 objects. So here's your axis. You don't have to make it along something you've called the X or the Y. You can just say, there it is. Okay? So we're going to do gravitation without a huge amount of vector work, although a little bit. Yeah, in the problems that we do. Okay, so we need to know the separation of the bodies. So they're R apart. R is always what we use for a displacement or a general separation. It does not always mean radius. And then we just write down the force. So the force between them, F, is big G. This is another constant. I Ironically, it's a smaller value than little g. I never thought of that before. But big G is universal gravitation. Little g, F equals mg, is just at the surface of the Earth. That's what we'll be talking about. So big G, the mass of one, the mass of the other, over the separation squared. So that's the magnitude of the force. It's not the direction. Let's look at these real quick. So G is, it's literally, we call it big G. Okay, that's like its nickname. I think its formal name is the gravitational constant. But it's just big G. And it's 6.67 times 10 to the minus 11. So it's very teeny. Gravity is a very weak force, Newton meter squared per kilogram squared. It has to be newtons, meters squared underneath, but cancel those meters squared and kilograms squared on top. Yeah. R is the separation between the centers of the objects, if they're spherical. So you know, in all this physics we've been doing, we've been mostly thinking of objects as point masses. So really, if they're point masses, then it's just from object to object. If an object is spherical, gravitationally it acts like it's a point mass. So the main thing is, if you're dealing with something big like a planet, for this formula you would go from the center to the center, right? Not from the surface to the surface. So that'll become important eventually. And then M1 and M2 are, of course, just the masses in kilogram. Well, everything's in MKS units, as always. And then the direction. That's the hard part, right? What is the direction of that force? So I'll say that F, the direction, is attractive toward each other. Toward each other. So if we draw it, there's one of them, and we would start to label it. We always like to have this consistent labeling scheme. So I would call this F1-2, or no, 2-1. This is the force that 2 applies to 1. Right? They attract each other. And this is F1-2. Force 1 applies to 2. Right? The force being applied to 2 has to be drawn on top of 2 for a reasonable drawing. Let's see. Okay. So that's it. So we're done. Right? That's the whole lecture. The whole lecture derives entirely from that formula.